Now, we've seen that regularization in the form of norm control so far introduces a bias. So why does it help? Well, we're going to try to answer this by analyzing the bias-variance trade-off for ridge regression. And it's a particular type of vector bias-variance trade-off that we're going to use, and I'll explain it first. So this video will do the following. I will first explain how we get this vector bias-variance trade-off. Then we will see how it works for the ordinary least squares solution. And then we will do the same analysis for ridge regression, and we will compare the results to those of ordinary least squares. And we will see exactly why we have this trade-off between the bias and the variance, and how we can reduce the variance using ridge regression. Even though the bias goes up, if we pick the right value of the regularization or penalty coefficient, we can improve our solution. And quantitatively, this means reduce the mean square error defined in a certain way. So let's first remind ourselves of what the linear regression setup is. We have a random sample of IID pairs, xi, yi from I equals 1 to n. So this is, we can call an input, and this we can call an observable target or output. We assume a linear model. So that means that we have basis functions phi I of x, and there are p of them. So we have phi I from I equals 1 up to p. Now I can define a vector of these, we call it phi of x, as follows: phi 1 of x to phi p of x. And our model is f theta of x equals a linear combination of these with some coefficients theta I, phi I of x. And if I define a vector of these, so if I define theta equals theta 1 to theta p, then this can be written as this, the dot product of this vector with this, which is what I have here. And then we include some additive noise. So our observable differs from this regression function by some noise epsilon. And I can equivalently write this for all of the data as follows. So I take all of my targets, y1 to yn, put them inside a vector, call it bold font y, take all of the errors, epsilon 1 to epsilon n, put them inside a vector and call that this bold font epsilon. And then this is equal to some matrix, this matrix here, which we call a design matrix, phi, times this vector theta plus this. So what is this matrix here? Well, phi is equal to the vector of basis functions phi at x1 as the first row down to the vector of basis functions at xn as the last row. So equivalently, we can write this for all of our data in this compact matrix form. Okay, so what do we do in ordinary least squares? Well, we minimize the empirical squared error. So based on our data set, these pairs here, so we have realizations of these, we minimize the square error between this and this prediction. So this design matrix times theta predicts y, because we assume that this error conditioned on phi has zero mean. And we can write that square error as this quantity here. So this is the 2 norm of the difference between this and this. And explicitly, this is equal to y I minus, let me call it, so f of x, f theta of x is this thing here, f theta at xi. So it's the sum of these squares from I equals 1 up to n. So over all of the data points. So this is precisely this. We are minimizing the empirical square error. So that's what we do in ordinary least squares. What about ridge regression? Well, in ridge regression, we minimize the same square error, but we add a penalty. to this objective. And that penalty is some regularization or penalty parameter lambda greater than 0 times the 2 norm of theta. So this has the effect of driving down the magnitude or the norm of theta, this problem. And it introduces a bias. We can no longer claim that the expected value of this phi times theta with the ridge solution is going to be equal to y. Okay, so we're going to ask ourselves the following question in this video. How does this regularization, adding this term, change the bias and variance? In ordinary least squares, we know that we have no bias. We have variance, but we have zero bias. So what happens in the case of ridge regression? Our regularization that we're going to focus on is precisely this regularization, ridge regression. Now, for any estimator, let's call it theta tilde, so this is going to be a function of our random sample. Its mean squared error, or mean squared estimation error, let me call it MSE, or theta tilde, is defined as this expectation here, the expected value of the 2 norm difference between our estimator and the true value theta. And using a simple trick, we can decompose this into 2 parts. I've done this in a previous video. And this part here, let's leave that alone for a second. This will turn out to be something that we relate to a variance. This part here, well, the inside here, what do we have? Well, we have the expected value of theta tilde minus the true value. And that's how we define the bias. So that is precisely the inside here, inside this norm, is the bias. And so what we've got is the norm of the bias of theta tilde squared with the square norm. Now, the expected value of this is just going to be this thing itself, because this is no longer random, right? This thing inside here is no longer random. So its expected value is the thing itself. So we've got the mean square error defined like this is equal to these 2 terms. And this is our bias variance trade-off. But let's go a bit further. That first term is what? It's the second moment of the residual. The second moment of the difference between theta tilde and this expected value. And we can interpret it as a type of variance. So even though theta tilde is a vector, and so it doesn't have a variance, it has a covariance, which is a matrix quantity, we can define a scalar notion of variance and call it total variance. And we define it as precisely that first term, this expectation. And we can simplify this as follows. So this is what? This is the expected value of this 2 norm. So it's the expected value of this vector dot product with itself, or this vector transpose itself, same thing, standard in a product, the dot product. And this we can write as the trace of this times the transpose of itself. In other words, this is an outer product. This is a standard trick that we use. And this is, you can see this from some simple linear algebra. It's a little bit messy, but it's pretty straightforward to see. So this dot product can be written as the trace of this outer product. Right? So this trace we can take outside. And so what we've got left inside is the expected value of this outer product, which is precisely the covariance matrix of theta tilde. So this total variance turns out to be the trace of the covariance matrix, the sum of the diagonal terms. So let me remind you what a trace is. So if we have a matrix, right, we have diagonal terms here, whatever is here and here, well, let me not put 0, let me put x and y up here. The trace is simply the sum of these diagonal terms. That's what the trace means. So this total variance is the sum of the diagonal terms of the covariance matrix of theta tilde. And so we end up with this following bias variance formula. The mean square error in our estimator is the trace of the covariance matrix of the vector estimator plus the 2 norm of its bias squared. Now, in ordinary least squares, the expected value of the estimator is equal to the true value, so the bias is 0. And I previously showed that the covariance matrix is given by this quantity. And so what do we get? We get the mean square error is sigma squared times the trace of this, because we can take the sigma squared outside. Okay, let's now move on to ridge. So let's start with the expected value of ridge. What is its expected value? Well, its expected value is going to be, well, what is theta ridge? What's the solution? The solution is this thing here. Right? That's how we define. So if we put lambda equals 0, we'll get back to this will become, again, the Moore-Penrose pseudo-inverse times y, which is precisely the ordinary least square solution. But with the lambda there, we get this, and that's the ridge regression solution. Okay, now what is y? Y is equal to design matrix times theta plus epsilon. So let's put that in here. So we get this once we condition on phi. So importantly, we are conditioning on the design matrix. Now equivalently, we are conditioning on all of the inputs, right? So what we're really doing is conditioning on all of the inputs, but our design matrix is a function precisely of all of these inputs. That's how it's defined. The way it's defined is a function of all of these. So equivalently, rather than conditioning on these, we can condition just on phi. It's equivalent. So the expected value of ridge, the ridge solution, condition on phi is given by this. Now, once we condition on phi, this is not random, so we can take it outside the expectation, and we get the expectation of y, which is this, conditioned on phi. Well, this, once we condition on phi, is not random, right? So we get, this becomes this quantity here plus the expected value of epsilon conditioned on phi. Now, in ordinary least square solution, one of the main assumptions we make is that the expected value of our vector of errors conditioned on all of the inputs or on phi equivalently is the 0 vector. So this is the 0 vector, and we end up with just this, which is the expected value of our ridge solution. So you can see here already that this is not 0. If lambda is not 0, sorry, if this is not theta. If lambda is not 0, this is not going to be equal to theta. If lambda is 0, we get this to the minus 1, which will cancel this, and it becomes theta. So what is the bias then in this case? Well, we've just calculated the expected value of theta ridge condition on phi. And it was what? It was phi transpose phi plus lambda I inverse times phi transpose phi theta, right? And we've got to subtract from this expected value theta, and that will give us the bias of theta ridge condition on phi. Well, we can take theta as a common factor and put minus I multiplied by theta, which is what I've done here. Now this is what? Well, now let's take this as a common factor, right? So let's take it outside. And if we do that, inside we're left with this term here, and then we've got minus. Now, if we take this out as a common factor, we're going to have to put what's inside here over here multiplied by I, because when we multiply this by this, we get I. Okay, now where does this lead us? Well, what's inside here? We've got this cancelling with this. And so we've got minus lambda I left. So we've got minus lambda times this, times I, so it doesn't change it, times theta. Okay. Now, to understand what this implies, we're going to look at the eigenbasis of this matrix here, phi transpose phi. Now, we know it's a symmetric positive semi-definite matrix, so it will have an eigen decomposition of this form. We can write phi transpose phi as some matrix U times another matrix sigma times the same matrix U transpose. So what are these matrices? Well, sigma is a diagonal matrix. And what does it have along the diagonal entries? The eigenvalues sigma I of this matrix. So sigma takes this form: sigma 1, the first eigenvalue of phi transpose phi, then the second eigenvalue down to the last eigenvalue, which will be sigma p. Right? Sigma p, because phi transpose phi is a p by p matrix, right? So we're going to have p eigenvalues. So, and everything else is 0. So this is what sigma looks like. It's a diagonal matrix with the eigenvalues of this matrix along the diagonal. What about the matrix U? Well, U is an orthogonal matrix or unitary matrix, and its columns are the eigenvectors of phi transpose phi. So it will satisfy the following properties: U times U transpose is the same as U transpose U. We have orthogonal columns and rows, which will both be the identity matrix. And this tells us that U transpose is the same as the inverse of U. So these will be very useful properties going forward. So now we have what? Well, we have the bias is equal to minus lambda times the matrix phi transpose phi plus lambda I inverse. Well, let's replace this now with this eigen decomposition. Right? So what do we have here? Well, we can go from here to the following. Why can we go from here to here? Well, let's look to see what's inside here. What have I done? I've taken U as, if we do U times sigma times this, we will recover this term here. And then do U times lambda I times U transpose. And what will we get? We'll get U times lambda I times U transpose. Well, that's just a number, so that becomes lambda times U times I times U transpose. Doesn't change it, so it's just U transpose, which is, this thing is I. So we just get lambda, right, times I. So we get back to this. So we can write this like this. Okay, so now what have we got? We've got minus lambda times U times the inverse of this thing here, times U transpose. Why? Well, the inverse of a product like this, so if we have matrices A, B, C, and we want to find their inverse, that's going to be equal to C to the minus 1, B to the minus 1, A to the minus 1. So applying that to this, we've got, let me clear this up a bit. So we need to take the inverse of what's inside here. So first we start with U transpose inverse. So we're going to get, but U transpose is the inverse of U, right? U transpose is actually the inverse of U. So we've got the inverse of the inverse, which is U. So that's the first term. Then we've got the inverse of this, that's the second term. And then we've got the inverse of this, U, this. But we know that this is U transpose, and so we get this here. So these are the three terms. That's how we get from here to here. Now, what is this matrix? Well, sigma is a diagonal matrix. So sigma looks like this. We've got sigma 1 down to sigma p. And we're adding to that lambda I. So we're adding this matrix, lambda along the diagonals and 0 everywhere else, just like this matrix here. So what do we end up with? We end up with lambda plus sigma 1 down to lambda plus sigma p. Now, what's the inverse of a diagonal matrix like this? It's very simple. It's just the same matrix, but we do the reciprocals of these. So this becomes 1 over lambda plus sigma 1 down to 1 over lambda plus sigma p, and everything else remains 0. Right? So that's what I have here. So I can write this matrix as diag, or diagonal matrix, 1 over lambda plus sigma 1 to 1 over lambda plus sigma p. So this is notation for a diagonal matrix. And these entries that you put inside these brackets refer to the diagonal entries because everything else is 0 anyway. So we've ended up with this here as the bias. Okay, now in order to make more sense of this, I'm going to write this in the eigenbasis. Right? So first of all, when lambda equals 0, what happens? Well, the whole thing becomes 0 because we've got lambda here. And so the bias is 0. So we recover the ordinary least squares bias, which is what we should recover. Now, this shows that ridge shrinks the magnitude of theta towards 0. But how exactly does it do that? And in order to see this, we're going to write that the bias in the eigenbasis. So what is the eigenbasis? Well, the eigenbasis of this matrix phi transpose phi. That's what we're talking about. Now, it has eigenvalues sigma I and corresponding eigenvectors, let's say ui. And this is from I equals 1 up to p. So what does this mean? Well, these eigenvectors will form an orthonormal basis for vectors in all vectors in Rp. In other words, for Rp, Euclidean space with dimension p. So that means any vector in Rp can be written as a linear combination of these eigenvectors. So any vector v in Rp can be written as a linear combination sum ai times ui from I equals 1 up to p. That's what this means. So we can write theta in this eigenbasis. Right? Now, since these are orthonormal, we can write it as follows. We can write it as, so theta can be written as the sum from I equals 1 up to p ui. And what are the coefficients? They're going to be the orthogonal projections of theta onto ui. Right? That. So this is an orthogonal decomposition of theta in this eigenbasis. Okay, so we can write the bias like this. Right? So this is nothing more than a little bit of linear algebra. You can actually see it from here with a bit of matrix manipulation that we get this sum here. So what do we have here? Well, we have two factors in this sum, right? So what is that first factor? Well, let me start with this factor. This we can call a signal in the direction ui. And what is it? It's the component of theta in the direction ui. Right? This tells us how much of theta lies in the direction ui. And then the second term here is a shrinkage factor, this lambda over sigma I plus lambda. So what's going on here? Well, let's have a look. Right? So we've got the bias of theta ridge, which is going to be a vector, is this sum minus this sum. So the bias will shrink the true value, right? So we're going to get a lower value compared to the true value, right? Because we've got a minus here. By how much does it shrink each of the direction? How much does it shrink theta in each of these directions? This is what this is telling us. Right? So it's shrinking it by this times this. So in the direction ui, we are shrinking theta by this times this. So let's analyze these two. Well, this we can't really analyze, but we can analyze this term here. So this will depend on how much of theta lies in that direction. Maybe very little of it lies in that direction, in which case this dot product would be very small. But maybe a lot of theta lies in that direction. Component of theta in this direction is large, in which case we could be potentially shrinking it a lot. Now, if we have a small eigenvalue, then this shrinkage factor becomes approximately 1. And so we're going to get a large bias. Or we could get a large bias. Depends on the size of the other factor. But if sigma I is large, then the bias will tend to be smaller because this shrinkage factor will be smaller. So in the limit, this could become 0 if this is much bigger than lambda. We will get or tend towards a smaller bias. But as I said, the shrinkage also depends on the component of theta in the direction ui, how much of it lies in that direction. So ridge only introduces bias where there's something to shrink. If there's nothing to shrink, if the component in that direction is small, well, it's not going to shrink it anyway. But generally speaking, what ridge will do is it will shrink very aggressively in those directions where sigma I is small. We have small eigenvalues. And I will come back to this later because this relates to instability and multicollinearity. So let's now move on to how ridge affects the total variance. So first, let's calculate the following. What is theta minus its expected value, condition on phi? Well, this is theta, ridge. The expected value we calculated before, it's this quantity. So we've got this minus this. And y is phi theta plus epsilon, right? And so what do we have here? Well, let's see. We've got this times phi transpose times phi times theta, and we've got minus the same thing. So that will cancel. So basically, this term here will cancel this whole term here, and we'll be left with this times this times this. This is what I've written here. So let's now analyze this. So what is the covariance of theta ridge condition on phi? Well, by definition, it's this expectation. The expectation of this outer product, theta ridge minus this expected value. Now we just calculated this as this quantity. So it's the expected value of this quantity times the transpose of itself. Right? Now, if this is conditioned on phi, this whole thing here, we can take outside the expectation. Right? So this whole thing here, from here up to here, we can take outside. Similarly, this whole thing here, once we've conditioned on phi, we can take outside the expectation here. And so what we're left with inside, so this goes outside, becomes this. That goes outside, it becomes this. What we're left with inside is the expected value of epsilon times epsilon transpose condition on phi. But we know that by our assumption, the expected value of epsilon condition on phi is 0. And therefore, by definition, the covariance of epsilon condition on phi is going to be this expectation, right? Because the minus this just disappears in both of these, epsilon and epsilon transpose. And what is that? The covariance of epsilon condition on phi? Well, we assume that it's sigma squared I. That's the standard assumption we make in Gauss-Markov. So this we can replace by sigma squared I. And the sigma squared we can take to the front. And so we're left with an I here. And that changes nothing. So we can just ignore it. So what we've got is this times this times this, right? Times sigma squared. So now let's use the eigen decomposition. So we got to this point here. Now let's substitute for this eigen decomposition. So we get this. We substitute it here and here and here. So we get this expression here. Now let's see what's going on here. So we're going to use the same factorization I used before. So this whole thing can be written like this. It's what I did before. And the same here. We write that like that. So now what have we got? Well, we've got, so let's do the same thing as before. So when we take the inverse of this, we're going to take the inverse of this first. But this is also the inverse of u. And so at the front, we'll get a u. Then we've got the inverse of this, sigma plus lambda I inverse. And then we've got the inverse of this, right? So we've got u minus 1, right? And that's multiplied by u here. So those two will cancel. We're left with sigma there. And then we've got the u transpose, right? Now we're going to do the same thing here. So the inverse of this whole thing, well, that's u to the minus 1 which is U transpose, to the minus 1, which is U. U transpose is the same as U minus 1. And U is orthogonal anyway, so this just becomes the identity matrix. And then that's multiplied by sigma plus lambda I to the minus 1, that part. And then we've got U to the minus 1, which is U transpose. So that's how we get from here to here. So we've got the U, this inverse, times sigma, times this inverse again here, and then U minus 1, which is U transpose. Okay. Now what do we have? Well, let's look at the multiplication of these three matrices. So what is that going to be? Well, we've got sigma plus lambda I to the minus 1, and I showed before that that's going to be, so what's that going to be? It's going to be 1 over lambda plus sigma 1 down to 1 over lambda plus sigma p. And that's multiplied by sigma, so it's multiplied by this matrix here, sigma 1 down to sigma p, right? These are all 0. And what will that give us? Well, that will give us the diagonal matrix, sigma 1 over lambda plus sigma 1 down to sigma p over lambda plus sigma p. And this is still diagonal, everything else is 0. And then that's multiplied by this again. And so what we'll get is sigma 1 over lambda plus sigma 1 squared down to sigma p over lambda plus sigma p all squared, which is, we can write as diag, this thing here. So that's how we get from here to here. We replace this product here with this diagonal matrix. Okay, so what does this tell us? Well, first of all, this tells us that the eigenvalues of this covariance, right, are given by sigma squared times these individual terms here. Why is that? Because we know that this is a positive semi-definite matrix, so it will have an eigen decomposition, and it should look like V times sigma, let's say sigma prime, not to confuse it with the one for phi transpose phi, times V transpose. Well, let me take these inside, sigma squared and sigma squared, right? So what have we got here? Let's compare this to this. Well, U and V must be the same. So actually the eigenvectors of this are exactly the eigenvectors of phi transpose phi, right? So this is actually U. It turns out to be the same matrix. But what's sigma prime? Well, this has to be a diagonal matrix. In an eigen decomposition, this will be the eigenmatrix of the eigenvalues of this. So let me call those sigma 1 prime down to sigma p prime. Well, there's your sigma 1 prime and there's your sigma p prime. So all the eigenvalues take this form. They're related to the eigenvalues of this in this way. And the eigenvectors are exactly the eigenvectors of phi transpose phi. But this is not the most important thing that we're interested in. So first of all, let's set lambda equals 0 and we will recover the OLS variance. We can see that, well, we can see it from here, but it's easier actually if we just look at it from here. We set lambda equals 0 in here. This will disappear, and we'll get this times the inverse of this, that will cancel, and we'll get sigma squared phi transpose phi minus 1, which is exactly what we had before. Now let's calculate the total variance, and that's going to be the trace of the covariance matrix. So the sigma squared we can take outside the trace. So we get sigma squared times the trace of this matrix, right? Now, the trace of a matrix, we're going to use the following fact. The trace of two matrices multiplied together, A times B, is equal to the trace of B times A. Right? Now, let's think of which way am I doing it here? So let me call this matrix A, U, and let me call this product, let me call this B. So this is our A, and B is this diagonal matrix times the transpose of U. So this has to be equal to the trace of B times A. So we put A second here and B first. So these two matrices multiplied together is what I'm calling B. So that's how we get from here to here. But U transpose U is the identity. So we're left with this diagonal. And so we've got sigma squared times trace of diagonal, which is sigma squared times the sum of all of these. We get this thing here. That's the trace of the covariance matrix. That's the total variance. That's how we defined the total variance. It's a scalar summary of the quote-unquote variance of the estimator theta ridge. Right? Now, if we set lambda equals 0 in here, right, we will get the ridge total variance. And what is that? It's simply sigma squared times the sum of the reciprocals of the eigenvalues of phi transpose phi. And this has to be greater than the total variance we just calculated from for theta ridge, which is this thing here. Now let me take sigma I as a common factor here and rewrite that like this. So this is the same thing as this. I'm just using sigma I as a common factor here. It comes outside, sigma I squared cancels that with one of these sigma i's, and we get 1 over sigma I, and this factor. And you can see that this factor is clearly less than 1. We've got 1 plus a positive number divided by a positive number. So this is going to be less than 1. So for each I, this is less than 1. So this sum has to be less than this sum. So what does this tell us? Well, it tells us, first of all, that the larger we make lambda, the smaller will this be this total variance. We can see that clearly from here. So what does ridge do? Well, ridge reduces the variance of the estimator, or it has a smaller variance. So it introduces a bias, but it reduces the variance. And the optimal value of lambda will find the right balance, meaning it will reduce the variance by more than it increases the bias. So ridge shrinks variance in directions corresponding to small eigenvalue sigma I. Why is that? Well, let's see by what it's shrinking it by. Well, it's shrinking it by this factor here. So each 1 over sigma I gets shrunk by this factor. The smaller is sigma I, the bigger will be this factor, 1 over 1 plus lambda over sigma I. So it will shrink more aggressively those directions in which sigma I is the smallest. Right? And these are precisely the directions in which ordinary least squares will have the highest variance. And this is also an explanation, although I've covered this before, of why ridge helps with ill conditioning. So we looked at this before, but we can see it perhaps even more explicitly here. So this is how ridge stabilizes ordinary least squares and helps with especially the problem of multi-collinearity.